Hey, top of the morning, top of the evening, you guys. I don't know what time you're watching the video, but I hope wherever you are, you are doing well. So today we're just going to be looking at this Euclidean geometry problem. So my learners just wrote the assignment a couple of weeks ago, so you can take, your time to sort of like read through, right? So you can just pause the video and then take a look at the question, right? So you can see that we are given a tangent which is CD. So this is a tangent, so you must already expect tan-chord theorem to apply. The likes of tangents from the same point if you've got more than one tangent, but by the look of things we only got one tangent, so meaning that we are only expecting tan-chord theorem to apply. And also we're given, let's just carry on reading. Okay, so to CD is a tangent, fine. Chord AB is produced to C, all right. Chord B equals to chord AD in H, right? And then the most importantly, we also got parallel lines. Okay, we've got AC being parallel to FD, right? So meaning that we must expect to have what? Number one, corresponding angles. Number two, we must expect alternating angles. Number three, we must also expect co-interior angles. Okay, so this is the three concepts that I can think of right now as far as parallel lines are concerned. So if there's anything else that I left out as far as parallel lines are concerned, please drop it in the comment section. Okay, so and we've been told that AB, right? AB is equal to EF, all right? Those are two chords. AB is equal to EF, okay? So now what does that mean? As soon as we've got chords that are equal, we must expect them to subtend equal angles either at the circumference of the circle or at the center of the circle. All right, so equal chords subtend equal angles. Okay, so you must expect that whether these equal chords are subtending angles at the circumference of the circle or the equal chords are subtending angles at the center of the circle, those subtended angles will always be equal. Okay, so now I think we've got everything, right? Except that they also went on to say angle D4 is equal to X. So there's our angle D4, X. And they went on to say angle D1 is Y. Okay, so from here to there, that is Y. Okay, so I think we've got everything we need now. We've read the information thoroughly, and we have managed to sketch in the things that have been said from the information sheet on our diagram. So we're definitely ready to answer. Okay, this is what I definitely recommend, that before you start answering, you must check what is given and also think about the implications of what is given. For instance, if you've got alternating angles, what should you expect? If you've got equal chords, what should you expect? Okay, so on and so forth, right? So now let's start. 2.3.1, they're saying name with the reasons 3 other angles equal to X. So you can see that there's X is leaning on this tangent, which is CD, and the chord BD. So basically X is an angle between a tangent and a chord. Do you understand? And remember, an angle between a tangent and a chord is equal to the angle in the alternate segment. Do you understand? So now we're going to only focus on the triangles that are formed from chord BD. Do you understand? In other words, triangles that are starting from B and D. Okay? Those are the triangles that we're going to focus on. They must be starting from B and D. So you can see that from B and D, you can have this angle over there. Okay, so basically this is the triangle, right? That has got BD as its side, right? Right, so BD is one of the sides of this triangle. Now let's also look for another triangle whereby BD is one of the sides, right? I hope you said BDE, right? This triangle over here, BDE. Okay, so we've got two triangles which have got one of their sides as BD. Do you understand? So now the angle which is formed, right, by moving away from point B and D to the circumference of the circle. Can you see? We can start from here and go to the circumference of the circle. The angle that's formed, that's A. So meaning that angle A is equal to X. Tan chord theorem. And now let's check. From B and D, we can start and actually get to angle E, which is also on the circumference of the circle, right? So meaning that angle E2 is also equal to X. Same reason. Tan chord theorem, right? Tan chord theorem. So, but now the problem that we've had, right, the problem that I've noticed is when I was marking is that so let me just write this down. Angle A is equal to X, tan chord, and angle E2 is equal to X, also tan chord. So the thing that I really noticed was that most learners said angle H2 is equal to X, and their reason was tan chord, right? Now the problem with this is that if you check where H2 is located, this vertex here is not on the circumference of the circle. Yes, the triangle BHD has got BD as one of its sides, right? But the problem is that it's not on the circumference of a circle. In other words, if H2 was somewhere here, if the triangle was going like that, right? If the triangle was going like that, and then this is H, then that angle there would be equal to X as well. You see? So that's the problem that we have. This tan chord cannot apply. If you check, A is on the circumference of the circle, and this the triangle, whereby A is found, has got BD as one of its sides, and also F is on the circumference of a circle. In fact, triangle ABD, all its vertices are on the circumference of a circle. Also in triangle DFE, all the vertices, what triangle am I looking at? Triangle BDE as well, right? Triangle BDE, its vertices are on the circumference of a circle, okay? Which is why E2 is going to be equal to X. But another misconception was that angle X is equal to angle F, right? Which is a misconception as well, because if you check, DE is not BD. Do you understand? So if we had F being formed as a result of D and E coinciding with BD, then we'll say F is close to X. So in other words, this chord here is not equal to BD. That's the problem. Okay, so because you can see that there's no way you can start from BD and get to F. You can't start from B and D and get to F. You know, that's really the challenge that we're facing right now. So yeah, so that's just one of the misconceptions that I've come across, that learners are thinking D4 is close to F. Tan chord theorem. In fact, F is equal to the whole of D4 plus D3 plus D2. Do you understand? In other words, the whole of this, right? The whole of that. But now, if we are saying the whole of that, you can see that now our chord of focus becomes what? The chord that we would really focus on, it would be D, F, right? If the chord we're focusing on is D, F, then D4 plus 3 plus 2 becomes the angle between the tangent and the chord. But also D4 plus 3 plus 2 won't be equal to F, but will be equal to the angle in the alternate segment, which is basically this. Do you understand? So yeah, hopefully that makes sense. So now we've just identified two angles that are equal to X. Let's see if there's any other angle which is equal to X. So we said this is X, and what else is X? The E2 is X as well. Okay, so maybe we might want to make use of the fact that we've got, we've got what? We've got parallel lines, right? Because you can see that angle A is actually alternating with angle D2. So angle D2, right? Angle D2, which is this angle over here, you can see that there's a Z that is being formed. All right, there's a Z that is being formed over there. All right, so D2 definitely, that is an angle which is equal to A. They alternate. So D2 is equal to angle A is equal to X. Why? Because these are alternating angles. So AC is parallel to FD. Some learners, they don't mention the what we call the parallel lines, right? Which is very important, because now, like, we can never have angles alternating if there's no parallel lines. Yeah, to put it simply. Right, so okay, now we've figured out that okay, there's also D2, which is X. Okay, and so what needs to happen next is that we need to now answer 2.3.2. They're saying show that DBE is equal to X plus 2Y. So now let's check what is DBE. DBE, so DBE, so that is basically D3 plus D2 plus D1. All right, that is D3. So it's angle D3 plus angle D2 plus angle what? D1, right? Angle D1. So we've been asked to show that this is equal to what? X plus 2y. All right, that's what we've been asked. So we're just going to take a look and see what is going on, right? So we did speak about what's this thing? We did speak about D2 being equal to X, right? Angle D2 is equal to X. And remember what we said, that D2 is actually equal to angle A, right? The alternate, there's parallel lines. So DT is equal to X, that's been proven. And angle D3 is equal to Y. Now this is where, remember we said equal chords to obtain equal angles? Yes. So you can see that the chord, right, the chord FD, not FD but FE and AB, they actually subtend D3 and D1, okay, and both chords are equal. And remember what we said about equal chords, that they subtend equal angles. So FE and AB are equal chords. As a result of that, D3 is equal to D1. Okay, so we're going to say D3 is equals to Y is equals to angle D1, right? Resonance equal chords subtend equal angles. Okay, so you can see that angle D1 was already given to be Y, right? This was already given. So remember what I said, that the angle that they're talking about is actually equal to D3 plus D2 plus D1. Okay, so angle D3 plus angle D2 plus angle D1, that's basically equal to Y plus D2. Remember we said it's X. Now D1, we also prove that's already been given, you know, to be Y. So now that just becomes 2Y. Let's put it in the right order, X plus 2Y. So we've answered the question, you know, show that DBE is equal to X plus 2Y. Okay, and then they went on to say, prove that BCDH is a cyclic quadrilateral. Okay, and remember, there's three ways to prove that a quadrilateral is cyclic. One, opposite, you know, angles supplementary. Angle A plus angle B equals to 180, so on and so forth, when the opposite angles add up to 180. Right, also when there's angles in the same segment. Okay, number 3, when the exterior angle equals to the interior opposite angle. Okay, so these are the three theorems that we can actually use to prove that, you know, a quadrilateral is cyclic. So now we need to, you know, identify the quadrilateral that they're talking about. They're saying BCDH. So here's our B, there's our C, there's our D, and there's H over there. Okay, so we need to prove that this quadrilateral is a cyclic. Okay, so I don't know how we're gonna do that, right? But obviously we need to use what we already, you know, found in you know, the previous questions to extend from that. Yeah, so remember we found you know, DB, and I mean BDE, right, which is D3 plus D2 plus, you know, plus that. We found that to be what? We found that to be X plus 2Y. Okay, so we need to decide, you know, whether we're going to be using one of the three. Opposite angles are supplementary, of which I doubt it's going to work. You know, we don't have any given angles. Number 2, angles in the same segment. Angles in the same segment, not too sure. But you see 3, it could actually work. Yeah, it could actually work. Yeah, I just don't know how, but yeah, it might work. So remember, we actually found D3, right? So D3 was found. Remember, we said that D3 is what? D3, we said that D3 is Y. Okay, we said that D3 is Y. So if D3 is Y and D4 is already given as D4 is already given as what? As X. That's D4. So D3 plus D3 plus D4 is basically X plus Y. Okay, let's jot that down. Angle D4 plus angle D3. All right, that's basically X. That's Y. I mean, those two are adjacent, so there's you know, nothing tricky about that. Okay, and remember that forms a vertex in triangle what? That forms a vertex in triangle ACD, right? Yes, that is a vertex in triangle ACD. So meaning that we can use D3 plus 4 and A to then find which angle? To then find this angle here, which is angle C. Okay, so yeah, and if we can show that angle, remember we showed that DBE is X plus 2Y, right? And DBE, that is angle D3 plus D2 plus angle DY. Okay, that is not the exterior angle of that, you know, quadrilateral, so we can't really use it to prove that this is a cyclic quad. Okay, so but let's just carry on with what we have. I wanted us to really find the angle C. So we're going to say angle A plus angle C, angle A plus angle C, plus angle, right? This angle here, which is D4 plus 3, is equal to 180 degrees, right? So, but now we don't have, you know, angle C. We do have A, which is X, plus angle C. So we just trying to find angle C. So this is X plus Y, which is equal to 180 degrees. Okay, so now that we've got that, angle C is basically 180 degrees minus what? Minus X, minus X again, and then minus Y, which is 180. Yo, you guys can't see. Sorry about that. So angle A plus angle C plus angle D is close to 180, and then X plus angle C plus angle X plus Y. Remember we said angle D plus 3 is, D3 plus 4 is equal to that. So now we can sum all the angles, and this is the same as 180 degrees minus 2x plus y. Okay, so that's our angle C. So now that we've got that, we can actually also we said that you know, angle E2 is X. Okay, and that was tan chord theorem. And we know that D2 and D1, so we know about D1. Okay, and we also went on to say that D2 is X due to the fact that it alternates with that. So basically in this triangle over here, all right, you guys will see where I'm going with this. In this triangle over here, what we can actually do is we can try to find H1, because H1 is actually an exterior angle of this, you know, quadrilateral. And if this exterior angle is equal to the angle C, of which we've already found, okay, is equal to the angle C, then would conclude that this is a cyclic quad. So angle H1, right, this angle here, plus angle E2, right, plus angle, and remember this is sum of angles in a triangle. So angle H1 plus angle E2, right, plus angle what? Angle D2 plus 1. Remember, this sums up to 180, because I mean D2 and D1, it's just this angle here. H1, the angle there. E2, the angle there. So you can see that they're in one triangle. Okay, that's why they sum up to 180. So that is sum of angles in a triangle. Okay, we've got that down. So, but remember, D2 is x. So basically D2 plus 1, it's x plus y. Okay, D2 it's x from that, and D1 is y. So angle H1, right, angle H1 plus angle E2, which is just x, plus x plus y, which is angle what? D2 plus 1. This must be equal to 180. So angle H1 is equal to, we're just solving the equation over there. Angle H1 is going to, so you take everything to the other side. Angle H1 is goes to 180 degrees minus, right, 2x plus y. So can you see that this is the same as that, right? Angle C and angle H1 are equal. Angle C and angle H1 are equal. So the exterior angle is equal to the opposite interior angle. So therefore BCDH is cyclic. What is the reason? Converse of exterior angle of cyclic quad. Okay, yeah, so that's how I would personally solve it. So this is, you know, one of those complicated, you know, questions in Euclidean geometry, but if you're patient, you can, you know, definitely get your answers correct. It's all about studying the theorems and all that, because if there's one theorem that's appearing and you can't identify it, you're gonna get into trouble, you know, like me in the past, right? Because yeah, Euclidean geometry has got no mercy. It doesn't care whether you've got experience and all that. You still need to know your theorems. Okay, so that's it for today, you guys, and I hope you've enjoyed the video. It was actually longer than I expected. So if you know anyone that might benefit from this video, please share with them, and comment in the comment section below if there's any issues that you are having, any positive feedback or negative feedback. You know, it's all welcome. So I'm out of here. Shout out.